Yeah, well, thanks, Cynthia. I'm really excited that so many people managed to show up on Saturday afternoon. It's sunny outside. You could be doing something else. So yeah, this is about, I think, an interesting connection between matrix completion and private singular vector computation I want to tell you about. And I try to keep the talk sort of lightweight because it's Saturday. But if you want more sort of hardcore details, I will use the whiteboard at your recommendation. So what is singular vector computation? Well, the first singular vector is just defined as the vector u that maximizes the norm of a times u divided by the norm of u. Okay, so that defines the top singular vector. I assume everybody knows that. And you can define the first k singular vectors recursively by searching or by maximizing the subjective function orthogonal to the previous vectors that you found. So those are the top singular vectors of the matrix. These are the things we're interested in this talk. Okay. So in my opinion, there's sort of three epochs in singular vector computation. The first one started with Cauchy in the 19th century in 1829 when he came up with spectral theory. And a lot of the math we're using today is still, from the 19th century. But we didn't have efficient algorithms back then. If you want efficient algorithms, you had to wait until von Mises discovered the power method in 1929, exactly 100 years later. And this was the first effective, first practical method for computing singular vectors. And then numerical analysis kicked in, and there were lots of results on efficient algorithms. Okay, so what are we doing today? I don't know about the 21st century in general, and I don't know what's going to happen in 2029. But today we sort of focus on data sets, and this is what this program at Berkeley is about and what this workshop is about in part. And we focus on properties of data sets and how they change singular vector computation, or the objective that we have. So for example, in this talk, what will be relevant is that a lot of data sets are very noisy or have missing values or come with privacy concerns. And we'd still be able to analyze them using singular vector computation while, making sense out of these objectives or out of these concerns. And so we're somehow back to where Cauchy was, that we have a lot of good questions, but we don't really know if they're efficient algorithms for them. Okay, so that's sort of the background. And one respective problem in this family is the matrix completion problem. It's a beautiful problem where you're trying to compute, or you're given a matrix like this, and you're only seeing a subset of the entries. You're not seeing all entries. Okay, it's just a subset of the entries. Don't think of the missing entries as zero. They're actually not there. Okay, so you don't know the full matrix, and you want to reconstruct the missing entries of this partially given matrix. And the way we're going to think about this is that we really want to approximate the dominant singular vectors of the unknown matrix. So not the subsample, but the matrix that we don't know, using the information that we have. Okay. So, and if we have the dominant singular vectors of the unknown matrix, then that also gives us low reconstruction error. Okay. So then we can also figure out what these entries are up to some error. And this is sometimes called the Netflix problem because they're it's not quite. We're not quite there yet, Malte. This is also called the Netflix problem because you can think of rows as movies and columns as users, and these correspond to user movie ratings. And if you could reconstruct the missing entries, you could do recommendation pretty well. Unfortunately, the problem in full generality is NP-Hardt. There's very little you can say without making further assumptions. But people have studied this problem quite a bit, starting with and have figured out assumptions that make the problem tractable. Starting with a beautiful work by Candace and Tao, people have figured out a set of assumptions under which you can actually prove interesting things about this problem. Okay, so what are these assumptions? I want to quickly go over them. The first one's very natural. You assume that the matrix is approximately low rank. Okay, so it's approximately rank k, where k is a parameter that's much less than n. Okay, so this is a very natural assumption satisfied by a lot of matrices. And that means that the top k singular vectors are very informative, and you don't need to know the rest. The second assumption we're going to make is incoherence. It came up in some of the talks, but I want to state it again. We're going to assume that the top singular space, so the space spanned by the top k singular vectors, is incoherent. And what does that mean? That means if you look at any standard basis vector EI and you project it onto the space U, you get a vector of small norm. Okay, so formally, if you look at EI transpose U and compute the norm of that, that's a short vector. Okay, so it's much less than 1. That's incoherence, okay? These norms are also sometimes called the leverage scores, come up a lot in a lot of settings, and you want them to be small, okay? It's an important assumption. Finally, you're going to assume that the subsample is nice, okay? So this is not the only assumption we need. We also need that the subsample is nice, and the easiest way of saying that is that the subsample is chosen uniformly at random, okay? Which is a strong assumption, but it's sort of dual to this incoherence assumption in the sense that these are really twin assumptions. So if you have an incoherent matrix, what you want is a random subsample. If you have a random subsample, what you need is an incoherent matrix. So together these make a lot of sense, and you can change them. If your subsample is biased, then I can tell you how you need to change the leverage scores so that you can do the same. Okay. So these are the assumptions that people proposed and are by now standard in this community. Sorry, all of them simultaneously. There's one more. We're also going to assume that it never rains in San Francisco. That too is a reasonable assumption, and we're just going to assume them. People now, I can say whatever I want, right? So people don't object to these assumptions anymore. Actually, I'm just making this up. So we don't need that it never rains in San Francisco, okay? My point here is that these assumptions are strong, but in hindsight, they led to an informative theory, okay? They led to very interesting theorems. And so I am actually not that pessimistic about these assumptions, even though they're strong. Yeah?
I'm not sure I understand the subsample uniformly random assumption.
So of a certain density, So you include every entry in your, so there are a set of entries that you know, and every entry is included with probability P independently.
I see, now I get it.
Sorry, so yeah, the way I think about this problem, you're given a subsample of the entries, and that subsample has to be chosen uniformly at random of a certain density. Or let's say every entry is IID chosen with some probability P.
And how many samples do you say?
So this is exactly the quantitative question. How many samples do you need to get a good result, to recover the matrix? That's exactly the question people studied in this line of work. Yeah.
Is there a nice geometric interpretation of the first condition?
The first condition?
The incoherence.
Oh, the incoherent. Yeah, so it somehow says that, another way to think about it is that all the singular vectors of the matrix are smooth, so they have small infinity norm. Because this is essentially what you're seeing there, EI transpose U is the ith row of the matrix U. And that has to have small norm. And since the row has only k entries, that means all the entries have to be small. So it's more or less equivalent to saying that the singular vectors have to have small L infinity norm relative, they're of norm 1. Okay. So that's one way to think about it. There are other ways won't really need. Okay, so these are the assumptions we're going to work with, which are standard in this line of work. And under these assumptions, there's been a lot of work, and it's a little bit hard to summarize it on one slide, but here's essentially what's happening. So there is a very nice, interesting algorithm, a convex minimization algorithm called the nuclear norm approach, which has amazing provable bounds. So they're very close to optimal, and optimal means the number of samples has to be something like, since Nina asked, I'm going to write this down more formally. So nuclear norm needs sample size about order k mu times n log n. Okay, so where k is the rank, mu is the coherence parameter, and as you can see, it's very close to linear in n, even though they're n squared entries. So you need much less than n squared. You need only about linearly many entries. So that's what nuclear norm gets you. It's very close to optimal. Unfortunately, the algorithm is very slow. It takes cubic time for it to run. It's a semi-definite program essentially. And there's an alternative approach called alternating minimization. That's sort of the method of choice in practice. It works amazingly well in practice, and the running time is incredible. It's nearly linear in the number of entries that you have, and unfortunately, the provable sample size bound. So the empirical sample size is great. But what we can prove about it is very not well understood. So the bounds here are very high. They're like k to the 7th and some other stuff. Okay, so one thing we're going to see in this talk, I should say that the first bounds over here that were due to Keshavan and Pratik, who's was here at the workshop and co-authors. And it was amazing that they could analyze this algorithm at all. So, even though this algorithm has been around for 10 years, it's only now that we have provable bounds for it. So this was a really nice paper.
Which examples are more less sensitive to outliers, like to the matrix being close to a rank error?
In practice, you always use alternating minimization. And in practice, you typically don't have, your matrix doesn't satisfy very strong assumptions. So alternating minimization is also very noise tolerant. Okay. So what we're going to see, one thing we're going to see in this talk is techniques that allow you to analyze alternating minimization in a better way. So we're going to say that we're going to see that we can actually get pretty close to the optimal. So we're going to get something quadratic in k instead of k to the 7th. And we're going to keep the running time at nearly linear in n. So I think there's now hope that we'll be able to get the optimal sample size at some point using alternating minimization. I think it's a true theorem, and we get a lot closer to that. Okay. So with that's basically one teaser, one thing you're going to learn in this talk. Again, this algorithm is based on alternating minimization. It's on the archive, recent work. But that's only one of two things I want to talk about, okay? And this is where Malte gets excited, because there's also the other Netflix problem, which is, privacy. And this is where, I inserted a dramatic reference to Narayanan and Shmatikov. So, please take note that I follow the convention in differential privacy. I hope you all attended Malte's talk at the rump session. So basically, you can also use a subsample of the matrix to re-identify users, which you might want to avoid. And so the question that we're also going to study in this talk is private singular vector computation. Okay, so the most basic way to formalize this is, given a matrix A, find or approximate the top k singular vectors subject to differential privacy. Okay, very simple. Can you do singular vector computation under differential privacy, and how well can you do it? And there's been lots of work, some of which you will see in an exciting recent work that Kunal's going to talk about in the next session. But it's been studied a lot since the early work by Avram and Cynthia and Frank and Kobe. So it's an exciting line of work, and I want to tell you what we can say about it. So using the same techniques using the techniques that I'll tell you about in this talk, we can get a nearly linear time algorithm for computing the top k singular vectors of a matrix under differential privacy with the following guarantees. If you want to talk about entry-level privacy, so differential privacy is going to protect against changing a single entry in the matrix. That's one privacy notion that you could come up with. Then we get the nearly optimal error dependence in terms of the rank k. So the target rank k, not the rank of the matrix, and the coherence of the matrix. Okay, so it turns out that for entry privacy, the relevant parameters are just k and the coherence. Okay, and without stating what the bound is, we get essentially nearly optimal dependence there. We only have a logarithmic dependence in n. Okay, so this bound is essentially dimension-free, which is sort of surprising that you have something that's dimension-free under differential privacy.
So Moritz?
Yeah.
So n is the number of people.
N is the number of people.
And the nearly linear time is in the size
of n. So it's the algorithm runs in time n times k squared times log n. Okay, good question. So yeah, I mean the optimal error bounds depend a little bit on what objective function you choose. There are multiple choices, so I don't want to bog you down with the formal details. But that's all in the paper. And this algorithm gets epsilon delta differential privacy. It does not work currently for epsilon 0. And I should say that this resolved the main question that Aaron and I left open in previous work, where we wanted to have the tight dependence for any k. We only got it for k equals to 1. Aaron used to offer at previous workshops $500. I still haven't seen those. I don't know what's going on. It's pretty stingy in my opinion. But okay.
Off the hook for the prize I offered for a negative resolution.
Right. John offered money for a negative resolution, but okay, then that's really not happening.
I thought that prize was supposed to be funded out of something established from the Twitter IPO. I thought it was fun.
Let's move on. So there's also, you can talk about, unit spectral norm or privacy under unit spectral norm changes. So instead of changing a single entry, you're protecting against a change to the matrix of unit spectral norm. Okay. So you can add and remove any matrix of unit spectral norm. That's a much stronger privacy guarantee. You're allowed to do much more, or you're protecting against much more. So that's the advantage, is a stronger privacy guarantee. The disadvantage is you don't get a dependence on the coherence. Instead, you get a dependence on n. Okay, so it's not sensitive to the coherence. The result doesn't get better with the coherence. Okay, I should say the coherence is in general much less than n, and often, depends on it only mildly. So having a dependence on the coherence is much better than a dependence on n. But anyway, it was shown by Michael and Michael Kaperloff and Kunal that the error that we get is optimal under this notion. And our algorithm also works for both epsilon 0, which is for which they proved the lower bound, and it also works for epsilon delta, where you get a root n improvement in the error bounds. And the running time is nearly linear instead of some larger polynomial running time. Okay? So this is one of what's going to be implied by our techniques in the privacy setting. And again, this is another paper that's on the archive if you want to see the details. So these are sort of the teaser results that if you understand the techniques of this talk, then you can prove these results, which might be nice. And so I want to talk about how we do this. Okay? And this is actually what I find most interesting. The main message of this talk is that there's one algorithmic idea, one algorithmic principle, which is the noisy power method. And it solves both alternating minimization and private SVD. So we can think of alternating minimization and our algorithm in the privacy setting as instances of a more general algorithm, the noisy power method. And by just analyzing the noisy power method, we can get bounds on both of these algorithms. Okay? You've also noticed that the incoherence comes up in both places, and it controls the error rates for both problems, at least when you talk about entry privacy. Coherence is the fundamental parameter, just like in matrix completion, where it's also the fundamental parameter. And we'll see that actually, the techniques that Aaron and I developed in the privacy setting for this problem, they actually solve some of the problems in alternating minimization. So some of the techniques that were developed in the privacy setting help us get provable bounds in the alternating minimization setting. It's nice that we can use privacy things that we came up for in the privacy setting outside of privacy. Okay, so this is the main message. I want you all to remember that because that's sort of what I'm most excited about. So let me talk about the noisy power method. Okay, what is the noisy power method? It's essentially an algorithmic template. Okay, don't think of it as an algorithm. It's more like a template that you instantiate. So the way this works is you have an input matrix that is n by n and symmetric. The assumption that it's symmetric is essentially without loss of generality. So for both settings, it's very easy to ensure. And you're also given a parameter k. This is the number of singular vectors you want to get right. Okay. So the way the algorithm starts is that initially you just guess an n by k matrix x0, which is just a random orthonormal matrix. Nothing fancy here. It's n by k. And then you iterate for t steps, for capital T steps. You do the following. In every step, nature, which is working against you, nature chooses a perturbation g sub t. Okay? And what you get to observe in every round is a matrix y sub t, which is equal to the product of a and x sub t minus 1, plus the perturbation that was maybe adversarially chosen by nature. Okay? So think of it as power method would just be a times x sub t minus 1. Noisy power method has this extra perturbation that we don't necessarily get to choose. In the privacy setting, we get to choose it. In AltMin, we don't. So think of it as nature choosing that perturbation. And then we orthonormalize the matrix. So we make sure that all the columns of xt are unit vectors and orthogonal to each other. And that's the whole algorithm. Then in the end, after capital T steps, you just output x sub t as your approximation to the top k singular vectors. Does that make sense? Is the algorithm clear? Too simple? It's too simple. People nod. Okay. So yeah, this algorithm is quite simple. And it's actually, the analysis is quite nice and pretty. And it uses an idea of principal angles. Okay, so the way you're going to analyze this algorithm is that you define an angle, a notion of angle between subspaces. And you argue that as you go along, the subspace that you have, the subspace spanned by x sub t, approaches the subspace that you want in this angle distance. Okay, so how do you define an angle between subspaces? It's actually everything you know about vectors carries through. Okay, so if you only know vectors, that's fine. It's good enough, that intuition. Okay, so remember, if k is equal to 1, then u and x are just vectors. Okay, they're just n-dimensional vectors. And so the cosine of the angle between u and x is just defined as, well, the inner product between u and x in absolute value. Okay, so pictorially, u and x are just vectors. The cosine is just the length of this projection of x onto u. Okay, and that's exactly more or less what you do for subspaces. So in general, if k is bigger than 1, you define the cosine of the angle between u and x as the smallest singular vector of the matrix u transpose x. Notice that's the same as what we had before for k equals to 1. In general, now u transpose x is a k by k matrix. It has k singular values, and you look at the smallest one. Okay, so that's the cosine of the angle between two subspaces. So just as a sanity check, suppose that this matrix, this k by k matrix, has a 0 singular value. Okay, so the angle the cosine is 0, right? The cosine of the angle. So sort of x is orthogonal to u. In this matrix case, it means that there is a non-zero vector in x, which is orthogonal to u. Okay. So in some sense, that should mean that these subspaces are, in a sense, orthogonal, okay, or have cosine that is 0. Okay, there's no correlation. There's a non-zero vector in 1 that's orthogonal to the entire subspace. Okay, so that's the definition. You can also define sine, the sine of the angle similarly. Here, what you do is you look at the matrix V transpose X, where V is the orthogonal complement of U, and you look at the largest singular value of V transpose X. Okay, and again, if you draw V to be this this vertical line orthogonal to U, then it corresponds to the length of the projection of X onto V. Okay, and you can check that you actually have 1 equals sine squared plus cosine squared, as you would expect from a definition of angles. So this is all very nice, and almost anything that you can say about vectors is still true for matrices. And the main notion that we're going to use in the convergence analysis is actually the tangent. Okay, so we're going to combine sine and cosine into one function, the tangent of the angle, which is the ratio of sine and cosine. And the tangent has sort of incorporates all the information there is, and it's the right potential function to look at. Okay, so what is the main convergence lemma for the noisy power method? Here's what you can show, and it's not hard to show. Let's first consider the case where GT is equal to 0.
Perturbation.
The perturbation is equal to 0, so it's noise-free. Let's suppose we analyze noise-free power method. Then what you can show is that the tangent between u and xt, so the tangent at step t, is less than the tangent at step t minus 1 times the factor sigma k plus 1 over sigma k. Okay, so the tangent is just sine over cosine. What I've written here is the tangent times a number that's always less or equal than 1. This number is always less or equal than 1, this ratio. This ratio is the tangent. So you just get that the tangent at step t is some number less or equal to 1 times the tangent at the previous step. Very natural, so the convergence rate is just the ratio of these numbers.
Just a clarification question. Your convergence is to the subspace spanned by the top.
That's exactly right.
Not to each one of them.
That's exactly right, to the subspace. So it may not be the case that the vectors individually approach each other, but the subspace overall gets closer. That's a great question. Yeah, Adam.
If you don't have a gap between sigma k plus 1 and sigma k, presumably you can still make nice statements about the power.
Absolutely. And the same analysis, in fact, goes through. And what you're going to do instead is that you choose the dimension of xt and u to be different. So you can argue things like, how quickly converge k vectors to the top 2k singular vectors? And then you would only get a gap between k and 2k plus 1. So you can generalize this to account for situations where you don't have a gap. Same picture. It's just slightly more difficult math. Okay, so now what happens if you have noise? It's quite nice. It's sort of exactly what you would expect. Just 4 minutes. Oh God! And you said you were going to be serious about enforcing time. Okay, so it's exactly what you would expect. So the sine gets perturbed by the projection of the noise term onto v, and the cosine gets perturbed by the projection of gt onto u, which is pictorially exactly what you expect. This length is the cosine. It gets perturbed by the projection of gt onto this axis. This is the sine. It gets perturbed by the projection of gt onto this axis. So it's exactly what you would expect geometrically, and that's the main lemma. So what can we do with this? We can, we have the hammer. We just need the nails now. I realize I'm a little bit over, behind, but so basically you can analyze alternating minimization. So the way alternating minimization works is that, you get a subsample of entries from an unknown matrix, and you want to find the unknown matrix. So you want to find the dominant singular vectors of the unknown matrix. And the way you do this is by solving a least squares step iteratively. So at every step you find a matrix Y, T, which on the observed examples, so which I'll denote by P omega, this is the projection onto the sample, minimizes the Frobenius squared error between A and the matrix that you have, so which is xt minus 1 times Y transpose. So this is an n by n matrix. You minimize the distance between these matrices over all Y. Notice this is convex because xt minus 1 is fixed and you only minimize over Y. That's why this is a convex program and you can solve it efficiently. Then you orthonormalize y sub t, and you go on. Okay, so essentially, on a high level, what it does at every step, it fits a rank k approximation to the matrix with respect to the observed entries. And you repeatedly do that and hope that you converge. Okay, so good. In the end, you output the last matrix that you obtained. So, okay, if you've never seen this before, it looks a little bit weird. All you need to know is that this update step that you do in alternating minimization, it can be written as a noisy power method update step. Why is that? Well, if you had full information, so if P omega was everything, you just knew every single entry of the matrix, then the solution to this least squared problem would just be matrix vector multiplication. So you would just get that y sub t is equal to a times x sub t minus 1. Okay, and so with noise, we can essentially do the same. We can say, well, if it were exact, it would just be the power method, but now you have this weird sampling error in there, so it's the power method plus the sampling error, essentially, at a high level. Okay, so the main hurdle is if we want to apply the convergence lemma, we need to control the norm of g sub t. And the way the norm is controlled, if you do the analysis, it's controlled by the coherence of this iterate. Okay, so at every step, the coherence of this iterate xt minus 1 tells you what the norm of g sub t is going to be. And so you need to control that. And that's actually a difficult part because how do you relate the coherence of this guy to the coherence of the underlying matrix? Okay? And so what you want is that if A is incoherent, then every iterate is also incoherent. This is the main property you need for incoherence. And we can argue this. Based on ideas that Aaron and I developed in the privacy setting. So you can show that there's some technique called smooth orthonormalization from this paper with Aaron that I can't go into, which will give you this coherence propagation property. So you can show that all the iterates that you come up with, they stay incoherent. If the original matrix is incoherent, all the iterates are incoherent. If all the iterates are incoherent, you have low sample complexity. So that's how the analysis goes. Good. So there's also something you can do in the privacy setting. It's a different argument that, again, was first used by Aaron and myself in another paper, and that I can now generalize to the k-dimensional case. So to recap, this is the important picture. The noisy power method is very powerful. It solves both of these very nice problems, in my opinion. And there's technology transfer between these applications in machine learning and privacy that I find quite interesting. And I did sort of manage to finish on time, so Cynthia's not going to kill me. I'm glad to live another day. So here are some conclusions and open problems, just briefly. So somehow what's actually happened a lot at this workshop is that we see that robustness or stability is kind of the common denominator between privacy and machine learning. And one thing I really like is to sort of find the right robust analysis of fundamental algorithms like power method, gradient descent, and so on. Even though these algorithms are so old, in the case of power method, there was actually a lot to be learned from understanding the robustness of the algorithm. And this is also something that Pratik suggested yesterday to get a good robust analysis of gradient descent. So there are lots of technical problems here. You can come talk to me afterwards. can give you some, or here's a list, or you can ask me questions. But I really want to finish now. All right, thanks.
Other questions? We can take some questions while Kunal sets up.
Yeah, Albert.
The sample size bound, you really talked about, is the reason for the sample size bound being large in some cases because that's what the algorithm needs to get something that looks good on the sample, or is it that you don't get uniform convergence in the sense of, normally you have this sort of thing where it suffices, I don't care by what algorithm, to find something that looks good on the sample, and then I know anything that looks good on the sample will be actually correct overall.
I think it's mainly the sample complexity comes in to control the norm of the error term. So the convergence rate kind of depends on these projections of the error term, and you really want that to drive. You can drive that down using more samples, and the difficulty here is that the algorithm is iterative. So the way you analyze, say, nuclear norm is just you analyze about a global optimum. Here you have to sort of do it step by step, and there's...
So with fewer samples, the algorithm won't even, on the samples, look good.
Yeah, you can't even argue that in one step you get progress. Yeah, Adam.
The form of the algorithm you gave, if I parsed it correctly, it's the matrix A has to be symmetric. Is that right?
That's right.
Is there a natural generalization?
Yeah, so the way what's usually done is if you have a rectangular matrix, you just do sort of B, this doesn't look like the right thing, B transpose, and then everything works with this matrix.
But then doesn't that, don't you pay a lot in running time for doing that?
Why?
Well, if B is very...
Factor 2, right? I mean...
Well, it depends.
Oh, if it's very skinny, you mean?
Yeah, so it depends what you're paying for. But
no,
A now has very few non-zero entries, but that doesn't mean you're running. But
it does actually.
But
because
your running time you can take advantage of that.
Yeah. It only depends on the input sparsity because you only do matrix vector products, so you only have to evaluate it against the entries that you know. You never write out this matrix. Is the short answer.
All right.
And there are other ways to deal with asymmetric matrices.
All right. Yeah.
Okay.
We'll get the rest of the answer.
Okay, so I should give up the microphone.
Again.